Hello everyone and welcome to We Meet at Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is how cable and PCB ferrites can help to prevent EMC issues. Our speaker is Laurent Völkel. He will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all your questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. The recording will be available at our website shortly. Now I will hand over to our speaker, Laurent, and I wish you an exciting presentation.
Thank you, Lisa. Hello, everybody. Just a short question, Lisa. Can you see my screen?
Yes, I can see it.
Thank you. So, hello, everybody. My name is Laurent Völkel. I'm field application engineer at Würth Elektronik. I work with Würth Elektronik more like 20 years. And today I will present something about EMC and something about EMC ferrites and how maybe you could prevent some EMI. First of all, when you think about EMC design, most of design engineer, like I was before as well, the EMC, it's mostly happening at the end when your device have been designed already. It's very important of economical point of view when you start to think on EMC issues, because as earlier you start in the development to put a small filter, to place a small pad for a cap, it will improve your design time, and especially you have not to redesign all the time the PCB. It's very important that the EMC design is starting already on the schematic before you make your first prototype or PCB. That's the message which I can tell you that I have in my experience. Is much earlier you start the EMC stuff and design and thinking about EMC, as less you have to redesign it, or maybe you have the luck, like I had once in my life, to pass the EMC test by first shot. I wished everybody to have experienced that experience because it's really wonderful. How you can check the EMC? That's a very difficult question, because actually it's not so easy to answer that, because if you want to make an EMC test, you need equipment, you need an anechoic chamber, you need EMI receiver, antennas, and even if you have all the investment of that, it costs you roughly €500,000. Do you know how to use them? Do you know how to make the tests by yourself? Really, it's not so trivial and not so easy to do that. Next point is also the EMC standard. Which EMC standard I must apply for my device? This is another huge problem, especially in automotive. When you look to the EMC requirements of different car manufacturer, sometimes I really think about and look on this graph and say, what these guys are thinking by using EMC level of the noise floor, almost on the noise floor of the EMI receiver. Very important to understand EMC, that when you talk about impedances, what means impedance? Impedance is not just the value in ohm. Z, it is 100 ohm, nice, okay. But what is it actually? The Z, the impedance, complex impedance, It is a calculation of root mean square of R square and XL square. The impedance analyzer measure above the frequency these two components of these two parts of the components, which is one is the impedance reactance and one is the impedance losses. Only just to know impedance is not enough. You have to know is impedance reactance or it is impedance losses. Why is that so important? Because when you are talking about filtering, you want to have an impedance in losses. And these losses, what make the ferrite with the losses? It doesn't can put that energy in a parallel universum. In the physics, we have the first law, which say the most important law, I say, energy never get lost. It's always transferred in another form. So this eddy current, magnetizing, demagnetized losses, what is happening in the core, it's make that these two vectors, which is electrical and magnetic field vector, get transformed into the heat. So ferrite take the EMI energy and transfer into the heat. But believe me, even if you take a very high sensitive thermal camera from Fluke or whatever, and you look on your ferrite, you won't see them hot. When you ever build a machinery where if you put the ferrite and the ferrite start to glow red, you don't have an EMC problem. You have a safety problem and run away fast you can. By automotive, if you make immunity test by 400 volts per meter or even sometime even higher, it could happen that the ferrite running hot if you have long cables and you have the resonance point reached. But mostly you should not make the ferrite to start to be hot. Very important that you know that when you design a electronic box, let be the ECU, and you put the ECU in the EMC chamber and is tested, all the requirements is fulfilled, everything is working good. As soon you put EMC device plus EMC device together, it's no guarantee that the whole system will be EMC compliant as well. So this is another problem that sometimes you fulfill all the requirement, but CE plus CE is not CE, and EMC device plus EMC device is not the whole system EMC device. So you don't have any other chance just to try to decouple this noise from one to other one, try to put some filter between each other, try to catch all the cable together, put some ferrite on it, and yeah, keep finger crossed that it works. Sometimes it's better to even over exceed the requirement and make, if you know that your device is sensitive data or something, to increase the immunity even higher like the EMC law are requesting or the customer specification. Most important thing when you talk about EMC issues is to recognize what kind of coupling do you have. This kind of coupling could be whatever, common mode or differential mode. This is the first step to find out before you start to talk about impedances or even components. Because if you have a common mode problem, you have to use a common mode choke. It won't have two inline inductors. If you have a differential mode, then you can put two inline inductor, or maybe you can use also the leakage inductance from the common mode choke if it's a sector wounded with a high leakage, and use that for differential noise as well. How to find out common mode and differential mode? I would say if you have a power supply with plus minus cable, you take this both wire, take a snap ferrite, put this snap ferrite on these two different cables, and look what happens. If you reduce the emission or you increase the immunity, it is 100% sure you have to fight again a common mode issue. Now, it's not a solution to put more ferrites or to put more winding. Look into the spectrum and find the right frequency or the right common mode choke and place that common mode choke in the PCB to this plus minus power supply and then retest it. If this snap-on ferrite on the cable did not help at all, it doesn't mean that the snap-on ferrite is not powerful enough or is the wrong company who supply it. It means you may have a differential mode problem. And now again, just for testing, split the wire, put one ferrite on plus, just for testing, put one ferrite core on minus, and then when you put plus and minus each one ferrite, it's a differential filtering, and you may have the impact. And the best solution, again, look to the spectrum, check which chip bit ferrite is good for this current, and then you use a chip bit ferrite on the right position where the noise is coming from and cancel this noise. We use different core material for our ferrites core, and you may wonder why we don't use the best one and that's it. Well, it is a difference between frequency issue, because depends on fragments, you can use different core material. Of course, this new nanocrystalline core are quite very good, but the costs are also the highest. Not everybody want to drive a Maybach Mercedes, right? And that's the reason why the most ferrites are nickel zinc, sinterite ferrite, and then we have this magnesium zinc, then manganesic zinc, and the newest one is this nanocrystalline core, which have an extremely nice bandwidth. The nickel zinc are are a very good bandwidth. It could be used up to 150 degrees Celsius. It's very simple uses, don't need to be coated because the surface himself is like ceramic and it's a good isolator. Don't need any coating on that. It's very good for cables and snap-on ferrites, also made in nickel zinc, a lot of them of those. Yeah, it's actually a quite very common core for EMI. The magnesium zinc, this is a little bit different to nickel zinc. The magnesium zinc is still non-conductive, but in a lower frequency is more powerful. So if you have issues less than 10 megahertz, it could happen that magnesium zinc is a better solution like a nickel zinc with many turns. If it's a issue less than 1 megahertz, this is something which is more lower frequency possibility like conductor emission issue or something like that. That is magnesic zinc and nickel zinc, maybe not the best weapon. It could be the mangan zinc. The manganese zinc, it need to be coated because the surface already start to be conductive. If you have a naked, I would say naked manganesic zinc and nickel zinc, both are black, you cannot distinguish which is which one. If you take the multimeter and scratch on the surface and you measure by nickel zinc the internal megaohm from the multimeter, by using that on magnesic zinc, you will measure some hundreds of kilo ohms, hundreds of ohms or kilo ohms of resistance because he start to be conductive. That's the reason why we coat them very well. This is a coating which is also in oven burned into to have even more layers to have a good isolation, and yeah, that's a must buy magnesic zinc. Now, if magnesic zinc is also too many turns and is not effective enough, then you have the last possibility to use nanocrystallines. Nanocrystallines in the past was made only just from two companies who had the license and the patent, but now is the patent done and everybody can produce them. They are the best in bandwidth. They are very high permeability, extremely huge AL value in the same size, can be used only until 125 degree, not because they are temperature sensitive, because they are not sintered material. The problem is that they are very, very pressure sensitive, and that's the reason why we not just coat them, we put them in a plastic enclosure. So you have actually a plastic box where all the ferrite core is inside, which is keeping them safe for vibration, hits, and breaking this very very um, uh, glassy product, which is very very, it's like glass, very simple. It's excellent for low frequencies and very nice bandwidth which you can cover with them. But definitely when you put a ferrite core above two wires like here, in fact, what you're building with this ferrite above the cable, it's actually a common mode choke. You can compare that with a common mode choke with bifilar wires just by using one single turn. So if you want to redesign your device where you have to use a ferrite core outside by the wiring and you want to put something on the PCB, you have to replace that using a common mode choke. Be aware that you use the same material because 99% of snap-on ferrites or ferrite tubes or sleeves, or nickel zinc, and 99% mostly are magnesic zinc by common mode choke. So you have to decide to use the same material for using this same frequency bandwidth and insertion loss. Where are the EMI noise sources? Well, EMI noise source could be a simple buck boost converter. And a buck boost converter like a SAPIC or Zeta topology, when you have here this synchronous switching, you can avoid the diode. You have no diode losses, but you have difficulties by EMI in conductor machine in buck mode, or by using in boost mode, you have on output um, conductor emission problem by buck mode in input conductor emission, by boost mode in output conductor emission. So you have to take care about these critical loop paths to make them short as possible and to put the right filtering on that. If you use a simple Zeta topology is quite very popular because you can use them in buck boost mode, and you have in a Zeta topology more the input is need to be filtered, because you see the inductor is charged and discharged always with a switch, and then you have a storage on the secondary side where you give the power out. So you have always an input generator conductor emission. When you look to the CPIC topology, the CPIC topology is not so aggressive on input, is more aggressive on output. You have to carry on by the CPIC topology to filter the rest ripple of your output. This is what you have to take care, and also how to place this Schottky diode with the capacity, output capacity, and the storage inductor. Both can be used by one single core, and you can use a double inductor, because always you use the core just a medium to store the magnetic field. You can use a twisted pair wired core with four legs or four pins, and you can use double inductors. You don't need to put two separate core inductors. If you look to your DC-DC converter, you have always the input capacity. If you know the parasitic of your input capacity, the ASL, ASR value, and you know also the parasitic from your input, you already can pre-estimate very simple what kind of conductor emissions you have to expect by the EMI measurements. Additional, when you look to the scope to your switching node, normally you should have the ideal rectangle signal, but you see always some overshot, some ringing, some undershot, some ringing, and you wonder in the EMC chamber, where the hell is coming this 300 megahertz noise, because my DC-DC converter is just using 500 megahertz. Well, components are not ideal. You have a diode here, and this diode have also ASL. You have the inductance, the storage inductance is also having some parasitic. The output capacity have some parasitics. And here in the resonant frequency, the high frequency resonance circuit, you may have some resonance, and this is this ringing which is happening. If you make a synchronous buck and you change this diode with the MOSFET, you can avoid this overshot, and you can make it smaller, and the ringing will be very short. And this is what I would recommend if you have the possibility to use a synchronous buck with two MOSFETs. Is definitely an advantage in terms of EMI. But anyhow, please take care that this path between output capacity and this MOSFET or diode, this PCB track should be short as possible, because that is the problem in the EMC chamber. If you take a EMI, not near field problem, a probe, and you find to try the problem where it's coming from, try to look on this path, and you will see this is very, very often the noise area. A nice example from a customer who did make a DC-DC converter for a very simple DC motor, and he did not pass the EMI. We saw he using two rod core inductance, which is quite very popular. I saw one design for an electrical seat, and I count on an electrical seat 62 rod core inductance. Every motor had two rod core inductance at least. It's simple, it's cheap, of course, but for EMI, maybe not the best one. And here, a storage inductance, definitely not a good solution. We decide for the customer to offer change this rod core inductance, put some shielded inductance, and float the ground here so flow this empty space with ground is a two-side PCB, and try your best. You go to the EMC lab back, and the customer give us a nice feedback that when you go to the EMC lab, the EMC guys, after see his version 1, he did fail. Look to the version 2, no filter. He asked him, where is your filter? And he said, no, I changed a little bit of PCB and some other components, and should work maybe. Let me try. And the guy was really not so motivated, the EMC guy, to measure it, because he asked him, what you think? Because you change your PCB from yellow to green, now you will pass the EMC test? The customer say, hey, I pay for that, come on, do it. And then when he start to measure, he start to be nervous, because you can see here the noise floor of the EMI receiver, and that was the noise which is generating from his machinery. So from here to here, just changing the color of the PCB. That's a good point, right? Well, actually, it was lucky punch. Honestly, it's lucky punch to get these results is not always the same. But this time, lucky punch was because of the ground layer and this shielded inductance. A shielded inductance is always welcome for storage energy. You can see here that magnetic simulation of these two different cores. Actually, you have a bobbin core in the middle, and then you have a magnetic field which is breaking out. On the other side, by the shielded inductor, you have the same bobbin core, but around the bobbin core, we put this shielding. And then you can see here that the magnetic way of the strong magnetic path is coming back very fast into the core using the shielding ring. That's the reason why a shielded inductance is excellent for storage and is very good for EMI instead of put a vertical of your PCB rod core antenna. It's not the best solution sometimes. You can see here a nice experiment made from my colleague in the lab here in our own lab. They took a DC-DC converter, switching frequency 2 megahertz, 1 amp output, and a 10 microhenry inductor unshielded version, and they measured the peaks without taking notice about EMI low, whatever, just taking notice of these peaks, and then take a soldering iron, desolder this inductance, take a same value but shielded inductance instead, and you can see what will happen. Bam, 90 dBm better. Only because the shielded inductors don't contaminate the whole system, and already in the conductor emission, you have a much better performance. Of course, in the EMI anechoic absorption, in making the radiated emissions, that's the right word, you can see the picture, they speak by themselves. You have always a better EMI in radiated emission if you use shielded inductance, which has less magnetic fields, stray magnetic field. The big difference between the PD and PDA, when we look in our portfolio, we have the same size. Outlooking is almost the same. This resistance, not a big variation, but they have sometimes difference. You can see that the big difference is by the socket, by the base. Sometimes by the PDA we use a plastic base, and sometimes by the PD series we use just a metal base. The big difference is in this case not the core all the same. Both have the same bobbin core, both have the same shielding. The big difference is by using this plastic base. By the plastic base, we connect the wire using welding. By using welding and not soldering, you have a much better resistance, excellent good reliability, and very high precision. But the disadvantage, you cannot use multiple wire like bifilar wire or multiple wire. If you want to use that, you must go by the metal base, and then you use a soldering junction. So by soldering junction, the advantage is only just because you can use multiple wire or bifilar wire, and that's the reason why it cannot be welded like by a single wire. The PD series, this nickel zinc, can go up to 2.2 millihenry with this metal base. This is also new ISAQ 200 tested, so it's also recommended to be used in car manufacturing or automotive application. By the PD2A, so the A is like automotive here in this case, are the bobbin core, which is very simple, I would say, cost-saving inductor, good for filtering. For storage, be careful. If you put everything in a metal box in a good Faraday cage, it will work. Or if you have very, very small currents, less than 200 milliamp, is not a problem. But anyhow, If you have a problem by EMI using a PD2A and you find out, oh my God, this is the inductor who make the problem, and you use the size 7850, so 7.8 by 70.8 and H only just 5 millimeter, you may have the luck that you can ask our sales guy for the PD2SA, which have the same bobbin core, the same footprint, same junction, just it has additional also a shielding ring, but it's only possible in this size. So if you have other sizes, it won't be possible. And of course, you cannot reach that high inductance value because you have the space for the inductance. Using the shielding already takes some space away. And yeah, it's a possibility in case you have less than 220 microhenry and it is this size, you may have the possibility to don't need to redesign your PCB because of the different component. If you want to put something like a chip bit ferrite, the chip bit ferrites are quite very popular because it's low cost, but if you have kind of inrush current, is starting engine inrush current or called low dump, you may have a pulse current through a standard chip bit ferrite, which is not defined when he will broke. I will say very simple. As soon you exceed the maximum current, it will broke. You can ask the MPSA series because they are pulse tested. The manufacturing is a little bit different, and you can use them in inrush for almost 20 times higher, like the nominal current. Have an extremely low this resistance. You can see here is going down to 4 milliohm, and they are excellent for pulse testing. Of course, you can see also that in the Red Expert, and you can see if you measure by a current clamp your inrush current, you can put in the Red Expert tool your current and your time, how many milliseconds it was, and then you can see if it's more like 100,000 pulses, it's good. If you want to sell to customer, which is only just 10 times withstand, it's also up to you. Maybe it's a timer for after 10 times switch on the engine to buy a new engine. Yeah, design tools. Which design tools could be used for this different application? I can explain this Red Expert is one of the good tool, not because it's just for Würth Elektronik. I can tell you, and I'm working for Würth Elektronik for sure, but um, all the values are not simulated values. Everything what you will find in Red Expert, it is really measured from colleagues in a laboratory. You have the possibility to see what is happening to this product before you put your own design. And if you put your current and your voltages and everything, you can really see what is the really losses of the component. We don't use the Steinmetz formula for calculating the core losses. We use measurement, and we have a algorithm which is 99.9 correct. And we have not only by 50% duty cycle a good measurement, we have on the whole range of duty cycle the right measurement. So this is a small evolution in the core losses because we include in the core losses also the skin effect, proximity effect losses, and not only just the core losses. And we can measure also alloys and not only just ferrite core. And Steinmetz formula is valid only for toroids. We don't use toroids, we use really cores, and that's the reason why I recommend LED Expert for measuring the core losses and calculating the right storage inductance. If you want to simulate something in a simulation tool, I can recommend the LT Spice. Linear technology have been bought from analog device for a few years ago, and now it's still the LT Spice. You will find a lot of our components in the library. If not, if you go to our toolbox, you can download the latest library. We have also a good library for LT Spice with really measured values with a network analyzer, not ideal components just by value, and not only just this resistance. We have the really replacement measurement by using a VNA. If you ask for S parameter, also S parameter is possible to get them. Anything else you can find in these beautiful trilogy books? We have already the 5th edition in the trilogy of magnetics, and the LT Spice book is also available if you want to make a good modeling and a good simulation. I saw already customer who can simulate already even ground planes like digital and analog ground planes, how to put them together, how to filter them from each other, and still to have a low impedance ground connection. This is all everything possible with LT-Spice. And please feel free and ask my colleagues in the sales to provide you this kind of books. Now I will go to the session of if you have any question, and if you put any question in this chat window, which I have to look on it, how to open it and make it bigger.
Yes, thank you, Laurent, for your great presentation. So now take a look at a question. Let's wait just a second. So I think we can turn to the first question.
Okay.
Are ferrites conductive?
Thank you for this question. Depends. It's really a good question because it really depends on the material. Like nickel zinc, magnesium zinc are not conductive. Manganesic zinc, it is conductive, and all the alloys like iron alloys, which are powder pressed together, they are highly conductive. That's the reason why we need to coat them. Even the nanocrystalline cores, they packed in the plastic housing. So nickel zinc and magnesium zinc, yeah, it's not conductive. You don't need to coat them. You don't need to paint them, whatever. You can use direct on the wire, but all others are conductive.
Okay, so the next one, which switching frequency should be used for a DC-DC converter for a good EMI?
Which frequency? They are not existing a good EMI switching frequency, of course. It's not possible to the best EMI switching frequency would be 0 hertz. So DC current, put a resistor, that's it. Efficiency, not so good. But if you go to the high-tech DC-DC converter, I can see that in the last time the IC's minimum switching frequency starting by 500 kilohertz, and they can go up to even 10 megahertz are existing chips for 10 megahertz switching frequency. The most important thing is by using a DC-DC converter by switching frequency is to put a filter calculated according to the third, fifth, and seventh harmonics. If you filter, if it's a buck converter on input, the third, fifth, seventh harmonics, I can guarantee if you have a good ground plane and no electric field problem, you have an excellent EMI in conductor emission, and it will be not a problem. If you don't take care and say, this is not my problem, this is the EMI guy problem who's measuring to fix it, it will be always a problem. But I cannot say there are a frequency where you can 100% be sure there's no problem is. As higher you switch, as higher will be the filter need, and as lower you go, as less dynamic you have, and bigger will be the inductor and capacitor. If you use a 10 megahertz DC-DC converter, you can make it in 1 centimeter square. If you use 1 kilohertz, you need the whole FR4 euro card size.
Okay, great, thank you. Let's take a look to the question field. There's some more questions.
I can read one here. I see, what is the right order of the components on the input of a switched mode power supply for automotive application? Schottky diode, TVS diode, ferrite bead. Thank you for this question. It's also a good one. Of course, first of all, you want to avoid the over voltage. For over voltage, you need a TVS, of course. That's the first thing. I need a TVS, powerful TVS, which are withstand this over voltage. After you put the TVS, you already can think about using this MPS-SA ferrite bead, which is for over voltage and over current protection, a kind of filter limitations of voltage, not so much, but for current, because it has a small inductance, and you can put your input capacitor, and then you can see if still needs something, you can put additional ferrite after the capacitor. inductor. So actually you build a T filter, the TVS is on the front. I would start with this. That would be, in my opinion, the best thing. If you need also for polarity, you can put the Schottky on front, of course. Yeah, I would start like you wrote, Schottky, TVS diode, the MPSSA, capacitor, and then put a 0 ohm resistor additional just in case you still need a second ferrite bead.
Okay, great. Thank you for your answer. So maybe we go to the last question. Are shielded inductors recommended to be used as a filter inductor?
Well, thank you for this question as well. You can use a shielded inductor for filtering as well. It's not a need to be used for filtering. It's also okay, unshielded version. But if you use a shielded version, you have the advantage that in the same package, in the same footprint, you have a better disc resistance, because with this shielding around the bobbin core, you may not need to put the same number of turns. You have a higher AL value, and you can reach the same inductance value with less number of turns. So ergo, you have a better disc resistance, you have a less losses on the filtering. But it's not a need to be shielded. If you can use still the unshielded version and you're fine with the losses on that, it's okay. If you want to improve the efficiency, if you are scratching on the edge of 98% efficiency, I would say use the shielded version, because you have also less disc resistance. So it's up to you, but it's not a need. I see somebody ask, what is the isolation voltage of nickel zinc core to make it conductive? You can't make nickel zinc conductive. It is isolator. It's like ceramic. You can't make them conductive. Make no sense. So there's no isolation voltage. You can test them by 4 kilovolts. By air, you have the air already more conductive, the air like the core himself. It's like an isolator, actually.
Okay, so great. Thank you. Now we are finished with this presentation. If there are any questions left, we will answer them via email afterwards. Thank you very much for your attention, and I hope you enjoyed our presentation. The
I
next
have a message. I have
Oh,
a
you have
message for you. If you have any questions for EMI, the most important thing in EMI, it is to never give up. It's always a solution. Don't give up. EMC, it can be solved. If you call our salespeople, if you call us in our hotline, we will try to give you a solution. Never give up. EMC is beautiful. Just you must understand. And as more your practice and more experience you make, you will like it like me. When I was design engineer and talk about EMC was not my pleasure. Today, after more like 20 years EMI experience, I say it's always a possibility to solve it. Just try to call us. And please watch our videos on YouTube channel. We have also a nice YouTube channel. If you want to be in contact with me, LinkedIn or Twitter, please watch the videos, and the rest, yeah, you can see all these PDF files from the website. Like Lisa, I think you will put on the website.
Yes.
Okay. Thank you for everybody from my side as well.
Okay, so thank you, Loran, for the message. The next presentation topic is how to select a suitable SMT ferrites, material, behavior, and key parameters, simulation with Würth Expert providing a new dimension for selection. We are really happy to see you there. So enjoy the digital days and goodbye.